Hello, pre-calculus friends. Here we are in Chapter 2. We're looking at Section 2.4, Modeling Motion with Matrices. In this section, we're going to be exploring different types of transformations. And this sounds like a big word, but really what transformations deal with is just the movement and the adjustment of a figure on the coordinate plane. So we're going to be dealing with a couple of different types of transformations, and they're going to be listed as the next few here. So one type of transformation is a slide, and it's exactly what you think it would be. So imagine having a figure like this triangle graphed onto the coordinate plane, and then you were to consider, in a sense, sliding that triangle to a different location. And so I'm going to do that by pasting a different triangle in a different location, or that same triangle shape exactly congruent in a different location. This would be considered a slide if you think about it, or a translation. So you translate from one place to another. The visual representation is a slide. And why would that work out? Because you can see that each of the points just got slid from one place to another, and it really is just a translation. You notice that the integrity of the shape stays the same. Everything is exactly the same, except it has been translated or moved from one place to another. The next one that we're going to talk about is a flip. And a flip or reflection. So a flip is exactly what you think it would be. It would be a reflection of that particular figure over, let's say, the X or Y axis. And you'll see that here. Let's say I start off with this triangle right here, and what I'm going to do now is flip it over the Y axis. So you can see that reflection has happened right there over or across the Y axis. So mathematically we'll call it a reflection, but it basically becomes a flip. The next one is a rotation, and it's probably exactly what you think. So a rotation is exactly what you think. It is a movement of somewhere between 0 and 360 degrees of a particular object. So that's one other transformation that we can have. And the next one is a dilation, which is an enlargement or a reduction. And so that can be easily demonstrated by, let's see if I can grab this and do just that. So this would be a dilation, enlargement, or reduction of a particular shape or picture or image. So down here in purple would be an example of my dilations. So the next thing is, okay, so these things can happen, but how do we do it, and how do we do it using matrices? Well, first we've got to get a couple of vocabulary words out of the way. The vertex matrix. Suppose you have a figure that's located on the coordinate plane and it looks like this. So we've got this quadrilateral. We can write a vertex matrix for this particular image. This would be the vertex matrix. And so basically what we're seeing is all the X values, Y values are lined up in this fashion into columns where each column represents a specific point. So a translation matrix is going to be the matrix that we're going to be using in order to do all of these different things. So we're going to have a matrix that will, or we're going to develop or discuss matrices that will help us translate, slide things around, reflect things over the X, Y axis, or even the Y equals X line, rotate things in 90, 180 degrees, and also demonstrate dilations. So that's what our translation matrices will be, and we'll discuss that in more detail soon. The pre-image is the image you begin with, and the image is the image that you end with. So the pre-image is where you start, the image is where we end. And these final two phrases, the reflection matrix and the rotation matrix, well, both of those are going to be matrices. Again, they'll be listed below that you'll use to do exactly that. Suppose quadrilateral ABCD with vertices A being -1, +1, B being 4, 0, C being 4, -5, and D being -1, -3 is translated 2 units to the left and 4 units up. So the first thing we want to do is represent the vertices of the quadrilateral as a matrix. And this is something we can do pretty simply by placing the values here in a matrix, and we talked about that earlier. The next thing we want to do is write the translation matrix. So now we have to consider what's going on. If we're going to be moving the matrix 2 units to the left, and then we're going to move the matrix 4 units up, moving the matrix 2 units to the left affects the x coordinate, and moving the matrix 4 units up is going to affect the y coordinate. So I'm going to grab this snapshot of what I have here of what the matrix is. And so the matrix is really going to be the matrix that we would add to this. We're going to add this to each of these different elements in the first matrix, or what we call the representational matrix of the quadrilateral. We're going to add all of these together, and then what we're going to result is asking us to use the translation matrix to find the matrices A prime, B prime, C prime, D prime, which is the translated quadrilateral. And so basically this is going to be the result. Remember earlier we talked about having the pre-image, and that would be this guy here, and then the image, which is the result after translation. So that's what we're about to have. And so our XY terms are going to be as follows. We're just going to add this whole row with this whole row. So -1 and -2 gives me a -3, and I'll keep going down the list as we add. And then I'll do the same thing for the y values, because I'm translating them up 4. They will go up 4, so I'd be adding 4 to each of those. And so we end up with this as a result. So this is the result, and as fancy as I want to be and graph it, I want to save a little bit of time too. So here for part D, it says graph the quadrilateral ABC and its image, and I'm just going to put this here. Let me scooch it around a little bit so you can see better. So there is our image, and so we can see the original one is here in blue, and then the translated one has been lifted up, and we see that we use, instead of A, B, C, D, we use A prime, B prime, C prime, and D prime. This can be really, really useful if you would memorize this piece. So we saw what it's like to translate, which is just to slide it from one place to another. But when we reflect matrices over the x, y axis, or even the y equals x line, then we're going to use matrix multiplication. And so you want to hold on to these matrices and kind of keep them in mind, because they're going to be really helpful when we work with the next section. Here in example 2, we're going to be creating an image by reflecting it over the y-axis. And so to create an image that appears to be reflected in a mirror, an animator will use a matrix to reflect an image over the y-axis. Use a reflection matrix to find the coordinates of the vertices of a star reflected in a mirror. That's the y-axis. If the coordinates of the points are connected to create a star. And so here are the coordinates, and the first thing we're going to do is put these coordinates in a matrix. So here we have the matrix written out. It's pretty large, but now what we're going to do is we're going to take that matrix and we're going to multiply it by the matrix for reflection over the y-axis. So you come back here and we remember exactly what's going to be multiplied. So that's the reflection across the y-axis matrix. By the way, if you look at what this matrix will do, it's going to change all of the x values to its opposite, and it's going to leave the y values the same, which is exactly what you want if you're reflecting something across the y-axis. So we're going to take that matrix and we're going to use it to multiply the matrix for the polygon that we have. Okay, so here's the setup, you guys. And now that we've got that, what we're going to do is multiply it together. But I mean, let's be honest. We know what it's like to multiply matrices. No fun. We'd be multiplying this times this, and that would be like the, you know what I'm talking about. We'd multiply those two together, add up the results, and then that would be like the first element here. But you can see what would happen. When I multiply this -1 times this -2, it's going to be a +2, and I'm going to add to it 0 times 4, which is 0. So I'm just going to get a +2. And if I continue in that way, let's say this one times this one, you see what we were talking about before. I'm really just going to get the signs of the x values changed. And when I go to multiply to find the new y values, you guys are going to see that the y value is going to stay the same. The 0 will obliterate the x value. So I'm not adding the x value to the y term. I'm just going to be multiplying, basically adding 0 to 1 times the y term. So I'm not saying that this is a short, it's not a cheat, it's kind of a shortcut because we get what's going to happen. So the result of the product of these guys will really just be, and I am so not trying to do this, that I'm just cutting and pasting here. Let's see if it'll work. Oh, that did not work at all. Let's try again. I'm going to cut and paste. No, I'm not. I'm going to just pause and you won't know that I'm doing this. Okay, so I'm going to pause you. Okay, so there we go. I just took the negatives off. I really just copied and took the negatives off because that's all that's going to happen and that's the result. So do I expect when you're doing this for you to actually multiply it through? Not necessarily. I mean, not if you can see a way to get around it. Here's some other helpful matrices that we should hold on to when we want to rotate a particular image 90 degrees or for a counterclockwise rotation around the origin. And so what we're talking about is having a shape here. Let me see if I can do this. I can't really demonstrate it easily, but let's say I had a shape here and I want to translate that shape around the origin or rotate that shape around the origin. These are the matrices that we'd use. So we want to hold on to these as we look at the next example. So in this example, we're going to be rotating a figure around the origin. And so we've got this figure, we want to spin it around, and we want to basically have kind of a freeze frame of what's happening in a couple of different places at 90 degrees, at 180 degrees rotation, and at 270 degree rotation. So what we're going to do is pull in those matrices that we know will help us to rotate. So I've rewritten those, and basically I'm just going to place, I wish you guys had the opportunity to copy and paste sometimes. Not like this is convenient, but it's a lot better than having to rewrite these things over and over again. So we're going to simply place these here, multiply them by each of the particular rotational degreed matrix, and then we're just going to get our answer. So you remember how to multiply these guys together. Let's go ahead and grab a highlighter. I kind of like doing this with a highlighter. So we're going to multiply this guy times this guy, and we're going to do that straight across, and you can see what's going to happen. Can you tell? Pause me and tell me what you think's happening. What I mean is, do you notice that this 0 is going to obliterate the current x value, and then this -1 is going to change the current y value to its opposite, therefore switching the y values for the x values, but the negative version. So instead of having, so when we do this multiplication dance here, we're going to end up with a -1, a -4, a -4, and a -3 for our x values. Let's see what's happening with our y values. So if I do that, let me get rid of this. If I come down here, and this is how I'm going to get my y values, notice that I'm just getting 1 times the x value and obliterating the y value and adding those together to get the new y value. I hope I'm not over talking y'all. But basically what this means is once I multiply this way down the list, I'm really just going to have the x values for all of the coordinates placed in the same place as the y values. So this is what happens when we rotate something 90 degrees. And if you think about it, it makes a bit of sense. The y value changes to the x value, but the negative version, and then we just leave the, well, let me say that again. The x value changes to the negative version of the y values, and then the y values change to what the x values were. All right. I don't know if you guys are buying it, but we're going to keep going. So again, let's just consider what's happening as we're multiplying. So as I multiply here, this first line times this first row times this first column, notice that I'm going to keep the x value the same. I'm not adding any y value because we're multiplying by 0. So I'm going to keep the x value the same, except the sign will be different. And so I'm going to change the sign of each. -1, 1, 2, and 2. And then let's see what's happening now with my y values. So what I'm going to do is multiply 0 times the x value, but then I'm going to multiply a negative times the y value. So you see what happened? We changed the sign of all the y values. So instead of having 1, 4, 4, 3, we're going to have a -1, a -4, a -4, and a -3. And finally down here, let's consider again what's happening when we multiply. So I'm seeing that multiplying this row by this column, I am actually going to get rid of the x term, but the y term will remain as the x values or as the x coordinates. And so this top row is going to be 1, 4, 4, 3. And then if I look at this second row, or how I'm going to get my y values, I'm going to be multiplying all the x terms by a negative, and the y terms will not be actually added to it. So -1 times 1 is going to be a -1, and I'm adding 0, and I'm going to continue with that. So you can see that each of these will change signs. All right, so this is the result of rotation around the origin. So an example for our final example, we have a trapezoid element P, and it has these vertices, so I made the matrix for us. Find the coordinates of the dilated trapezoid. Remember dilation? We get a picture, and then we can either make it larger or smaller. Find the coordinates of the dilated trapezoid with a scale factor of 0.5 and describe the dilation. So if the scale factor is 0.5, this is actually pretty cool because these are a little bit easier to do than even the addition when we just translate our matrix or our image around, right? So here's what we're going to do. We're going to multiply by the scale factor of 0.5. And so basically it's a bit of distributive property for us. So when we do that, we're going to get the image as we multiply the pre-image by 0.5, and when I do that I get a -2, 1/2, 3.5, -1.5 or -1.5, 1/2 again, a 2, 0, and -3. And so what happened here, if you were to graph both of these, what you'd see is that you have a shrinking or so the dilation is not a stretch, it's a compression of the actual image. All right, I hope that this was helpful. Use your textbook. Feel free to look through it because these are the same examples from your textbook. Just hoping that a live discussion will be of some help. All right, guys, listen, take care. Let me know if you have any questions, and I look forward to talking to you soon.